Now we're ready to look at some laws and that will help us to solve problems. And the one law that we're going to start out with is Coulomb's law, and named after Mr. Coulomb, who did a lot of research with regard to the different charges. And so the first thing we need to define is the magnitude of an elemental charge. So there's a certain amount of elemental charge either in a positive charge or a negative charge, electron or proton, and you can't get any smaller and you can't have anything in between, so they're basically little units. And that value for, we'll call it E sub C plus, this is the little electric elemental charge for a positive charge, is 1.602 times 10 to the minus 19th coulombs. That is the unit. Unit of charge. Please don't forget that. And for the elemental negative, it's going to be minus 1.602 times 10 to the minus 19th coulombs. Now, there are constants, and one is constant of free space, and really this is a what we would call a universal constant. No matter where you go in the universe, you'll always measure this value, and that's epsilon naught, and that's equal to 8.85 times 10 to the minus 12th. The units are coulombs squared per Newton meters squared. And this is called permittivity. Permittivity in space. And it's basically a measure of just how dense you can actually get an electric field or charges to react to each other, and it's a pretty small quantity. Now, many times we're going to be using a relationship based on permittivity, and we call that K of charge. We're using K again, so K with a subscript C, and that's 1 over 4 pi epsilon naught, and that's equal to 8.992 times 10 to the 9th, and since it's just the reciprocal and 4 pi don't have dimensions, then it's just the reciprocal of this, so it's going to be Newton meters squared over Coulomb squared. And we can approximate that to 9.0 0 times 10 to the 9th Newton meter squared per Coulomb squared. So let's take a look at two charges. We have a positive charge and a positive charge. We looked at a negative charge with a negative charge and a positive charge with a negative charge. And we said that like charges repel, and opposite charges attract. Now our subscripts are going to be very, very important here. So let's say I have force. Well, let's say this is charge 1 and charge 2, charge 1, charge 2, and charge 1, charge 2. Okay, for each of these different sets. And we're going to have force with a subscript 1, 2 on this side, and on the other side it's going to be the force with subscript 2, 1. So we need to understand what these subscripts are saying. So we have F12, force sub 1, 2, and that's going to be force on charge 1 due to charge 2. So you notice that this first subscript goes with the charge you're interested in, and the second subscript goes to the charge that's affecting the one you're looking at. And its opposite, force sub 2, 1, is going to be force on 2 due to 1. So subscripts become very important when we're doing these problems. We cannot get these subscripts messed up. Once you mess up the subscripts, the problem is wrong at that point. So we've got to be very careful what we do. Now Coulomb's law is going to look very familiar to something else that you worked with in Physics 215. So the force, and remember the force is going to be a vector, 1, 2, is equal to our constant K sub C times the magnitude of charge 1 times the magnitude of charge 2 over the distance between them squared times the unit vector. Now notice the subscripts. The force, in this case I have force 1, 2, but notice the subscripts for the vector r. It's opposite. So if I have a vector, in this case 2, 1, well that's just r2 minus r1. And let's say I have a three-dimensional vector that I want to know. Let's say we have r1 is equal to x1i plus y1j plus z1 k hat, I hat, j hat, k hat. R2 is going to be x2 I hat plus y2 j hat plus z2 k hat. Then our difference, well, you're going to take, remember the 2 would be what you would consider the tail, and 1 would be considered the tip. And if I'm going to subtract these two in this way, the definition would be x1 minus x2 I hat. And actually, it's probably better if I do it this way. Instead of saying 2 minus 1, let's say 1 minus 2. That makes better sense there. So it's the tip minus the tail. Tip minus the tail. Okay. And the, actually I could put an arrow here because it is a vector. And the r hat is just going to be the difference of these two divided by the distance. And that's just going to be x1 minus x2 I hat plus y1 minus y2 j hat plus z1 minus z2 k hat over the distance formula in 3 dimensions, square root x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. And we can rewrite this formula in this way, taking into account this definition. Let's see. So here we've just taken this square root and put it into our formula here, and that just makes this bottom part go to the 3rd power, and this top part then becomes here. Instead of having r hat, we'll have the r vector. So in some problems you'll see us do that. It's just a simplification, a little bit less work. So be very careful with the subscripts. Be very careful. Think of this as electronic accounting. You're going to have to just take and make sure that you keep everything in the columns that they need to be in. Debits with debits, credits with credits, if you're used to accounting. It's going to be very, very important. Now there's 2 ways of doing problems. If we are in 2 dimensions, we can simplify using component analysis. But if we're in 3 dimensions, then we have to use vector analysis. Have no choice. You can do vector analysis in 2D. Right? You can always do vector analysis, but you can't do component analysis in 3D. So our next few videos, we're going to be looking at an example in 2D and then in 3D, how you would solve a problem using these equations.